It's great to be back here. It's the first time I've been here in 5 years. I missed last year, unfortunately, but I'm thrilled to be back to give the latest update on JRuby and the work we've done. So let's get right into it. Most folks probably know JRuby is Ruby on the JVM. We've always had our primary focus is trying to be as compatible as possible and to mimic the same development experience that Ruby developers are used to. So we're not forcing them into a Java type of development process. We want them to be able to use the same command line tools, the same frameworks, the same libraries as much as possible. It's also bringing the JVM to Ruby. So all of the things that we've seen here today, all the things that are the reason why we love this platform, those can be beneficial to Ruby folks as well. And so while we bring the challenges of Ruby to the JVM, we bring the benefits of the JVM to the Ruby world. That has meant that generally JRuby scales Ruby applications better than the standard C implementation, even considering some of the JIT work that they've been doing recently. There's a tip over point where we will use less memory for a certain number of requests per second on a Rails app, for example. This can translate into real money for large applications. And so when Ruby developers, when Ruby apps get to a certain size, we are often the next phase that they go to. They move to JRuby to get better use out of resources and reduce some of their hosting costs. There's also a lot of fun stuff on the JVM that Ruby folks get out of JRuby. Multiple GUI frameworks that wrap existing libraries on the JVM. We have a Minecraft plugin framework that lets you write plugins in Ruby rather than in Java. We have an Android framework called Rubato that lets you build Android applications basically just writing Ruby code. And this is actually used for a number of point of sale, embedded terminals at various companies around the world. So who's using JRuby? Well, I don't know if we have tens of thousands of users, but there's definitely thousands out there. This is a rough cloud of logos from companies that have used or currently use JRuby for something mission critical. The kind of applications we see are, if you have one of those Rails web apps and you want to scale it better, well, that's a first possibility. There's a lot of folks that are building packaged software applications in Ruby that they then sell as commercial shrink-wrap software. We've got mobile and embedded use cases where Ruby doesn't really fit. We've got weird platforms like people running JRuby on OpenVMS and AS400 to avoid having to use what they used to use on those platforms. Building scripting support into existing Java applications. So using Ruby as the scripting language for some larger thing like a Jira or a Confluence. And oftentimes Ruby folks come to us just because there's better options for libraries. The ecosystem can be much richer. There's a lot more people contributing to it. Sometimes you just get a better experience using JRuby and using those libraries. So JRuby to me has meant an amazing sandbox to be able to play with all of the things that I have seen at JVM Language Summits over the years, all of these cool new features that come to the platform. Everything that I've seen here today, I can directly apply to some aspect of JRuby. And I can feed back to these projects like we've done with Invoke Dynamic, like we've done with other projects to bring our challenges and the interesting aspects of Ruby to your projects and help make both sides better. This also has helped me with a language and a community that I really love. I like the language Ruby, I like the community there. Being able to work on JRuby has let me bring the platform that I love and know well to all of those people. So JRuby to you, hopefully, is going to be an interesting test bed. I would say if you have something that you're working on at the runtime level, at the JVM level, and you're not testing against JRuby, well, you're missing a really huge opportunity to see how much we can torture it and break it. I have crashed the JVM more times than I can count. Going back and forth with folks on Invoke Dynamic, we found all sorts of optimization opportunities. The new demands that we have for native FFI, for lightweight threading, all of these things are going to be a direct give and take from JRuby to the projects on the JVM. So it really is a brutal test case, and I'm happy to break your stuff every day. So a little timeline for JRuby here. It started a little bit before I got involved in the project. It was kind of a pet project of a few developers. I came to it in 2004 after my first RubyConf. I did not know the language. I was at the conference, but I understood every slide, every piece of code without knowing anything about it. And so I was kind of hooked. I really liked the expressiveness of the language and the ease of development. So I started contributing to it. In 2006, we actually were able to run a full Rails application on JRuby for the first time, which involved a lot of additional libraries and a lot of contributions from many people. That year, Sun Microsystems took notice and hired us on so we could work full-time on JRuby. A few years later, we introduced the first JVM bytecode JIT for Ruby, which is the first, technically, first native JIT for Ruby that was ever created. We just dumped the bytecode and let the JVM take it. We started to have early production users, and that year was also the first year that we had the JVM Language Summit. Fast forward a little bit, we have done reworks of the compiler, reworks of the JIT, we've done continuous optimization, constantly trying to catch up or keep up with JRuby compatibility. It's a lot of work, and with really only 2 of us during these past 20 years, we've had to make some trade-offs along the way. So in 2024, we're excited because we've finally caught up on compatibility with JRuby. It's a constant battle, but we are basically ahead of the game. We have their next version of language and features basically done before they release it. So we're going to focus on optimizations and do more jumping ahead to Java 17 or 21 as our minimum. Now, one thing I noticed while I've been sitting here, this is the JVM Language Summit, right? So we go back and look at 2008. How many different languages were actually on the agenda as talks? We had the fan language. Some of these you're not even going to have heard of because they faded away or they're not interesting anymore. Fan, Groovy, Scala, Fortress, JRuby, of course. There was a PHP implementation. Attila presented the Dynalang framework for building dynamic languages. Clojure came with one of the earliest presentations. Of course, we had Python and Jython talks. There was a Link talk from some of the CLR folks. Kawa Scheme was presented here by Per. We had NetRex, we had Common Lisp, and we had one of our keynotes was about the Parrot VM that was being built for Perl 6. On the agenda in 2024, it's kind of lonely up here. There's not a lot of other folks that are talking about their challenges of implementing weird and unusual languages on the JVM. The code model, hat stuff is kind of languagey, but I'd really like to see if we can bring some of these communities back in here and see what's the latest from Scala, what's the latest from Clojure, what are the challenges of bringing these languages to new versions of the JVM. And so let's look at some of those languages. These numbers are based on the TIOBE ranking of language popularity. So Python being number 1, Jython essentially is dead. There's no development on it. It's stuck at 2.7. So we no longer have that implementation as a pure JVM version. Of course, there's work on the truffle side for some of these languages, but Jython is dead. Similarly, Rhino, Nashorn, basically no development, dead projects, not being developed for a pure JVM environment at all. There were VB implementations in the late 2000s. None of those took off. None of those are being developed anymore. The Quarkus, not Quarkus, but Quarkus implementation of PHP was a fairly complete implementation that, again, faded away. They ran into issues with C extensions and found that it was just too much work to try and keep up. JRuby is still plodding along. We have actual production users. We have customers now for JRuby commercial support. And we are continuing to push the edges of what you can do with Ruby and what the JVM can do for alternative languages. But it's like I've said, it takes a lot of work, and I really wish we could see more language contributors come back to the platform so we can collaborate more on these things. Looking at Ruby implementations over time. The JRuby standard implementation is still, high 90% of all Ruby deployments out there. We get the big ones that start to fall off and can't scale at that scale on that runtime. But JRuby continues to be the main one that people use. They have their ongoing JIT effort that they're working on. They are trying to reduce C extensions because that interferes with JIT optimization. They have all sorts of weird ways of doing parallelism without actually doing parallelism. Again, things that JRuby essentially does not have problems with. We're still trying to convince the CRuby folks to come over to our side. Rubinius was an implementation. It's kind of abandoned for about 10 years now. It was a from scratch, a meta-circular VM for Ruby that was being built by some friends of ours from the Ruby community. He just kind of lost speed and couldn't work on it anymore. We've all seen stuff about Truffle Ruby. Truffle Ruby has been very exciting at bringing extreme levels of performance and optimization to Ruby. Recently, it seems like development has slowed a bit, and as far as I know, there aren't any major production users of it. And then again, there's JRuby, silently powering that 1% of big and weird Ruby applications that just don't fit into the standard implementation. Now we're trying to push towards next generation JVM stuff, working on all the optimizations we've been stalling on for years, really trying to update everything for the modern JVM and see what that looks like for a language like Ruby. Okay, so getting into some of the nuts and bolts of JRuby and the design over the years. So high level, pretty typical for a language. We've got parser, we've got our compiler, we run the code, we've got a set of core classes, and ideally we use a lot of the same standard libraries that regular Ruby does. Starting out with parsing, this has been one of the big challenges for JRuby over the years. The Ruby language is extremely complicated. The parser is extremely complicated. Lots of context sensitivity in there. People love the way Ruby feels as a developer. As a parser, it's a nightmare. Just a bloody nightmare to make it work. Historically, there's only been one complete parser. It's an LALR parser based on Bison. Lots of little tricks in there that reduce the context insensitivity of it. We ported that to a parser generator called J that generates Java code, and that's how we've kept up for many of these years. Recently, there's been work on a new parser called Prism that we hope will align our work with the CRuby work, and we won't have to maintain our own parser anymore. I'll talk more about that in a second. So back in 2006, Nick Seeger, who was working with us on the JRuby project, generated some .viz graphs of the grammar for JavaScript versus Ruby. This is JavaScript. It's fairly regular, pretty easy to follow what's going on with it. And that's Ruby. And of course, this was 20 years ago. Ruby has added a whole bunch more language features since then and made a whole bunch of more nice-to-have features. So I expect that this graph would be even more complex if we looked at a modern version of Ruby. Trying to track this as part of our project is just too much effort. So we're looking to this new Prism parser I mentioned. This is a very simple, like C99-based recursive descent parser being written by folks at Shopify. There's several years of work on this, but it's largely complete at this point. It's very robust to errors, but sometimes misses code that's not technically valid and parses it in weird ways. We are actually going to be running this as our parser on JRuby. Initially, we will bind it with either a JNI wrapper or Panama where it's available. And on platforms where we can't do that, we've actually prototyped running Prism compiled as a WASM library running on the Chicory WASM implementation on the JVM. Now, initially, of course, that's too slow. We're only able to use this as bootstrapping so we can get the right native library booted up. But there is work now on a Chicory code generator to JVM bytecode that almost gets us comparable performance to a native library. So it's possible we may be able to run this native parser entirely on top of the JVM without calling out to native code. All right, so we've parsed our code, and now we have to actually execute this. All Ruby code starts out as source, and this is not something that's going to change. The Ruby workflow is that everything starts as source, it all gets parsed every time you start up, and you need to do this quickly. Get it parsed, turn it into whatever your internal execution format is, and then start going. Our eventual goal for performance is obviously to turn Ruby into JVM bytecode. And we'd like to make that happen as quickly as possible, but we also need to have reasonable startup time. And adding too many stages into that pipeline before we actually run the code makes it much slower for users and we end up with all sorts of startup time issues. And I'll definitely return to that in a moment. We do have a very high level of language compatibility. 99% something of the current Ruby versions, language specifications pass on JRuby. Of the core classes, we're also extremely high compatibility. We're hoping that this Prism parser will make that consistently easy for us to upgrade. All we'll need to do is upgrade to the new version of the shared parser that JRuby and us both use, and then we just fill in the blanks and make sure it compiles down properly. So looking at more graphically, we've got our Ruby code coming in on the left. We parse that and run it through our compiler and produce our own Ruby intermediate representation, our own instructions. And then we actually have interpreters for that. There's technically two interpreters. One we use as a quick let's get going interpreter at startup. There's a more optimized interpreter when we can't go all the way to bytecode. So we interpret for a while, then we JIT it into JVM bytecode, and then of course the JVM takes it and does the exact same thing all over again. Interprets the bytecode for a while, does some minimal compilation, some better compilation, and eventually we get down to native code for that Ruby code that came all the way in on the left. So interestingly, JRuby is basically, as far as I know, the only mixed mode runtime running on top of the JVM, which is itself a mixed mode runtime. So our goal here is to reduce the work at startup. We need to get the application up and going as quickly as possible, so we have our own interpreters. We eventually want to JIT compile to JVM bytecode only the interesting pieces of code. So once we pass some call threshold, we will turn that code into bytecode, pass it off to the JVM, and then hopefully the JVM continues from there. This brings some unique challenges to JRuby that most other JVM languages don't have to face. Obviously, we have an evolving representation of what a code body is, so we can't link directly to just the interpreter or just the compiled version. It has to be dynamic, and as we JIT our own code, we need to invalidate call sites and start calling the new version of the optimized Ruby code. We also have interpreter and bytecode frames on the JVM stack. And so when we take a simple piece of code like this, a method foo that calls bar, a method bar that we're generating a stack trace or we're capturing a thread dump here, when we run this in its entirety in the interpreter, we get something that looks like this. And of course, this is useless to anybody that's doing debugging of a Ruby application because we've got all of our interpreter frames, we've got all of our internal call site logic, all of this shows up on the JVM stack. Now that's not what we want. And of course, if it looked like this when JRuby users got stack traces, we would not have any users. They would not be working with us. So one of the first tricks that we had to figure out was how to do our own mixed mode stack trace on top of the JVM. So what we do is we maintain a separate set of interpreted backtrace frames for each level of the interpreter. As we walk the regular JVM stack trace, we look for certain markers that we know are associated with our interpreter, and then we pop frames off of our internal stack. Doing that, we can splice our internal interpreter frames with the actual JVM native frames and produce a nice backtrace that Ruby users are used to. We also include things like relevant top-level method calls in JRuby, so you can see that you're calling into our string implementation or our array implementation. And then, of course, if you call into other Java libraries, we don't cull those out of the stack. They will show up alongside other Ruby calls. So by using our little trick here, we can take an interpreted stack trace that looks like this, look for those markers, interpret method, interpret block, and generate something that looks more like this. And we can make this exact same sort of format, this exact same stack trace, even if it's interspliced with some JITted frames and some interpreted frames, because we just walk down the stack and rebuild it ourselves. Now, of course, we also compiled the JVM bytecode, but we don't want to have to maintain a separate heap stack or heap frame for that JVM frame. So we embed all the logic in the actual JVM trace. So this is an actual JVM trace from the JITted code from JRuby. We stick little markers in here so we know how to reinterpret it as a Ruby call. So looking at this foo call here, So blah is the script I ran, blah.rb. Right now using a little heart, a heart character as a marker that this is one of our Ruby JITted frames. We have put the word def in there so we know that it's a method definition of the foo method. And then because we might have the same named method multiple times in a given file, we have an index of each Ruby body as it's encountered during compilation. Similarly for the main script, instead of using a def, we use braces to indicate that this was a block or a closure. And then we encode the other parts of the main method so it fits into the JVM specification. And by doing this, we can pull everything out and turn this back into our regular Ruby trace, but also have it show up in the JVM trace as something readable. Now there's a trick here. These look like they are doing direct calls, but of course this is a dynamic language. These are all being routed through some sort of dynamic invocation mechanism. In that interpreter trace, you would see call site invocations, caching methods, calling through a call site implementation. The actual stack looks more like this. So this is where we make our dynamic calls using invoke dynamic. We build up a chain of method handles that finds a pointer to the target method, wires it up with appropriate argument shuffling, and then we see all of this on an actual thread dump. These are the real frames that are in between each of these calls. So that brings me to invoke dynamic. Invoke dynamic, of course, is what really makes JRuby work well on the JVM. Our bytecode output, if you look at the actual bytecode dumped from our JIT, it's essentially loads, stores, and invoke dynamics. Almost everything that we do at the JVM level, we have a custom instruction implemented in invoke dynamic. Of course, there's dynamic calls, but then there's lazily initializing things like strings and big decimals that are native to the language, compiling regular expressions and caching them as a constant in the code. We have a default execution mode that uses a minimal amount of invoke dynamic, just because some of the overhead of these method handles can be problematic when booting up. But we're really trying to work towards essentially being invoke dynamic all the time. Everything that we do is going to pass through invoke dynamic in one way or another. And so we see lots and lots of Lambda forms and method handles in our traces. So how does this work for performance? It's actually looking really good over time. There's a lot of optimizations we know we're missing, but we're continuing to improve this. So this is a comparison of two benchmarks, a Mandelbrot generator and a red-black tree, so something a little bit more application-like. And if we take on Java 8 and turn our invoke dynamic mode on, it's about twice as fast, and that has improved over time as invoke dynamic has gotten better, as the optimization of method handles has gotten better. We've seen continuous improvement. Less improvement on the red-black side, but again, this is just walking a lot of objects. Ideally, there's going to be a maximum where you can only walk these trees as fast as at a certain speed. And so over time, the improvements have not been as big, but we still see them get better over time. Now, one way that we know that invoke dynamic is working really well for us is when we look at something like the Graal VM's partial escape analysis. So if we take a look at our Mandelbrot example, once we actually get this all to compile down and everything inlines properly, we actually do see all of our float boxes disappear. So this is very exciting. It's very seductive, what we can do with escape analysis in this case. But in the cases where we can't actually inline everything, or there's a little too much variability in the call sites, sometimes that VM ends up being a little bit slower. So it's not a magic bullet that solves all of our problems. We're still trying to find ways that we can get more code to inline and get the VM to do more of the work for us. Okay. So are we fast yet? Well, it's a complicated question. As I mentioned, Truffle Ruby has done amazing work aggressively optimizing, aggressively splitting and specializing code. They're clearly faster at running small to medium Ruby loads than we are right now, and maybe faster than we'll ever be. But they use many, many times more memory. A benchmark that might use a couple hundred megabytes on JRuby will use several gigabytes of memory on TruffleRuby. That amount of specialization, keeping all of those different copied graphs in memory, has a cost. And it's not a cost that we've been willing to pay to optimize Ruby code. They also made a decision that they were going to support Ruby's C extensions. Initially, they did this by taking those C extensions and also shoving them into the optimizer graph. But that's an even larger amount of code. Now we're talking about tens of gigabytes of nodes in memory. It never even stabilizes. It's too difficult to optimize a large application that way. We are always trying to balance optimization with the usability of JRuby. It needs to start up well, it needs to warm up reasonably well, and ideally use not that much more memory than CRuby. We also kind of butt our head up against Lambda forms, like a lot of folks in here do. This is really like the fattest IR in the world. We're using this to build up little micro languages for our call sites, for all of these different invoke dynamics we do in our bytecode. And that's a lot of overhead early on. These things are executed just straight through for a while. Hopefully they turn into a little ball of native code or a little ball of bytecode that can be inlined and optimized, but it's easy to trip up this process. Some of these benchmarks I wasn't able to run on my current generation Mac couldn't run with GraalVM because some of the intrinsics needed to optimize method handles haven't been ported over or missing. So things don't inline, the performance tanks, very easy to break the inlining process for Lambda forms. We've also had complaints from users that this is a nightmare for tooling because we'll see different stack traces through these Lambda forms over time. Even if it's a call from foo to bar, we end up getting splits in the profile. We'll see 2 or 3 different versions of that stack because of the Lambda forms evolving, the Lambda forms change, and the profile gets thrown off and corrupted. It's also very hard to figure out why these things don't optimize. I had to kind of know that one of these core method handle invoke dynamic functions was supposed to be intrinsified and wasn't, to know why it wasn't optimizing on the Graal JIT. Most people aren't going to even know how to dig to that level. And so when something doesn't optimize or Lambda forms start to be a problem, it's very difficult to see what's going on. I'm hoping that we can find some more synchronicity with hidden classes here, with code models, try and bring a little bit more cohesion to the bytecode side and the method handle side without the fat IR of Lambda forms. Okay, so we can run code. Now we've got all this stuff working, we've got our whole pipeline, we've got invoke dynamic, and of course then startup time becomes the #1 complaint for JRuby users. Despite all of our tricks, we can't compare to what CRuby does. It's designed to start up fast. It's designed to get up and running quickly. Most of what you run at boot for CRuby is compiled C code. Everything we run is interpreted by the JVM for a good long while. We also have a significant amount of Ruby code that gets loaded at every boot. Of course, we're running from source primarily, so even core libraries that start up with JRuby have to be parsed and recompiled every time. It turns out that using our interpreter as the first stage of execution is faster than pre-compiling to bytecode and letting bytecode run cold. Our interpreter heats up more quickly, and we can run the interpreted code faster than slow interpreted JVM bytecode. So looking at what this actually means in practice, for -E1, just a basic like hello world, don't do any work on the command line, CRuby coming in at 0.05 seconds, JRuby many orders of magnitude more than that. And this is what people's first experience is when they come to use JRuby and try to use it on a project. Obviously not the experience we want. If we look at something a little bigger, like generating a new Rails application, CRuby can do that in 0.3 seconds. We take closer to 6. We have to find a way to fix this problem to get people on board with using JRuby as their primary runtime. So, of course, our first way of solving this is to just back off and turn off all the optimizations. we're back to a client mode. So JRuby has a --dev flag that turns off all of our JIT, forces the JVM to only use Tier 1, the C1 compiler, the old client compiler, tweaks us down to using parallel GC because initially it has less load and it gets up and going quicker. This actually has been our best way of speeding up the startup of JRuby. So we look at our generating a Rails app with our 6 seconds here down to under 3 by turning off all optimizations. Obviously, this isn't what you would want when you put something into production, and we've had a couple people that forgot to remove their dev flag when they did some benchmarking, but we're doing pretty well here. We'd like to be able to make the JVM do this without losing our JIT, without losing all of the other tiers, but currently, the fastest way to get up and going is to turn the JVM back into client mode. So of course, one of the first things that I wanted to look at for solving this is CRIU, in the form of CRAC, Coordinated Restore at Checkpoint. The idea here is that we can take a running process and snapshot it. Later on, we make a new copy of that process space, load it up into memory, and start executing basically from that point. The only cost of starting up then is restoring that image into memory and possibly reconnecting resources, sockets, I/O, file descriptors to get back to where we were. This is primarily a Linux technology. I know there is some work in the CRAC project to provide a reduced version that can run across platforms, but the best version of this depends on kernel level tricks to actually save off the entire process space and restore it. So if we look at our app generation again, we've got our --dev, and then we throw CRAC at it. And now we're actually getting into a competitive space as far as comparing to JRuby. Unsurprisingly, if we're booting right back in with CRAC, we're not having to do any of that early stuff. We can even train it, warm it up, do a little bit of extra JIT before we save the process, and then we're up and running much more quickly. Now, this is great, but most developers are running on Macs, and so only working on Linux is not really a good solution for the developers we're trying to reach. So then we've got Leyden, which is our new holy grail for startup. We've got many different levels of AOT that are coming down the pipeline. We've got this sort of super CDS. We can save off method profiles so we can immediately start jitting quickly again. Hopefully we save off some compiled code so we don't have to do the recompilation. Now we actually could consider pre-compiling some amount of Ruby code. We can give it to Leyden, we can give it to all of these super AOT features, and hopefully what we've given you as bytecode will be pre-optimized and we'll be able to boot up. It's not something that we've attempted yet, but we have done some experiments with early builds of Leyden on some of these loads. So taking a look at our hello world, we've got our 3 earlier examples. And in this case, CRAC, again, is only 0.2 seconds. A pretty good hello world startup for JRuby. Pretty good hello world startup for any language on the JVM. And then Leyden comes in. It's not getting down to the level of running as a snapshotted process space, but it's pretty good. And this is now our next best option across platforms. Assuming that this continues to go forward, maybe we can finally ditch our client mode and have a fast starting version of JRuby that still does all the optimizations. Similarly, looking at our app generation here, CRAC doing pretty well. Leyden less so, but still seeing a significant boost. I would suspect that this is probably more an issue of how I trained it ahead of time. Mostly I was just booting up JRuby. There's of course a huge amount of libraries and code that gets loaded when you generate a Rails application. I could also train those pieces in here and probably start getting down below our dev mode as well. Okay, so moving up from there, we've got our code running. Hopefully we're solving some of these startup issues. Now we have a core libraries issues that we have to do. We have to support the same classes and the same standard libraries as JRuby. Again, a high level of compatibility, something like 98% compatibility with all of the core of JRuby in JRuby. There's a lot of hidden complexity here though. For strings, in order to be compatible with the way JRuby represents strings, We can't use Java strings. We have a byte array representation and an encoding. Every string in the system could potentially be encoded differently, and so we have to mimic that same behavior. So we implemented all of our own string operations. And if we do that, then of course we have to implement our own regular expression engine. So we have a regular expression engine that can work directly against byte arrays with arbitrary encodings and different dialects. This was ported a long time ago from a JRuby or a C implementation called Oniguruma, and we have continued to maintain it over time. It's now actually used by several other JVM languages, including Nashorn, and I think Jython has looked at it as well. So those two libraries for this, we've got JCodings, which does all of the transcoding and character encoding logic, and Joni, which is our Java port of that Oniguruma regular expression engine that JRuby uses. Now I/O is also tricky. One of the things Ruby folks like to be able to do is interrupt threads that are blocked on I/O. If it's taking too long, I want to time out, I want to jump back into a piece of code and get back to work. With standard NIO channels, if you just make a blocking call and then interrupt it, the channel usually is dead at that point. You can't make guarantees about the state of the I/O or the internal state of the channel itself, so those channels get closed, which is not what we're looking for. That has meant we need to basically use selectable I/Os all the time, and unfortunately the JDK doesn't provide a complete set of selectable I/O. Only sockets and pipes typically are the ones that you can select against. That means that files, specifically for things like FIFOs, standard I/O is not selectable. Process streams are not selectable either. So doing an interactive subprocess from the JVM is basically impossible. The only way we can do this is by building our own versions of these. So we use actual native down calls for standard I/O, we do our own sub-process logic, and we have our own channels that are implemented on top of native file descriptors. That is based on the Java native runtime. I presented it here in 2013. This led to my first and only JEP 191, which was the precursor for Panama. So here we are, finally, what is it, over 10 years later, over a decade later, we're finally getting a native FFI, a native FFM built into the JVM based on work that we've done in the past, that we had to do. We've also seen recently, Jorn Verne from Oracle has done a version of our JNR framework that runs on top of Panama. And I haven't had a chance to get back to it recently, but we're hoping to bring that into an upcoming version of JRuby and see how that impacts our native integration performance. So obviously we're expecting that this is going to be better. From what we've seen, Panama is faster than just having our JNI-based FFI stub. Obviously this will improve our core I/O for some of these cases where we've had to re-implement it. But we're hoping it'll also bridge the gap between running Ruby FFI code and the C extensions that are a problem for all Ruby implementations. If we can get FFI calls programmatically binding C libraries to be just as fast as handwriting C extensions, we don't need to write C extensions anymore. And on the JVM, ideally, we don't have to write JNI anymore. We're also looking to use the code generation tools in JExtract, not only to generate our own internal JVM Java interfaces to these libraries, but as a library to help Ruby users generate Ruby FFI. The generator is only going to be useful to us for Ruby FFI if it can also generate JRuby FFI, and ideally that will help people start making the migration away from JRuby extensions. We have seen some early success stories here. This is the SQLite JDBC driver, which is what we use under the covers to handle SQLite support in Rails or other frameworks. They have done a proof of concept of this not using a JNI stub, but using Panama, and early results were good. It's about twice as fast for typical operations, typical database operations. I'd expect to see this improve over time, and that will pay off for our users too. So the last big area that's been a challenge for us, of course, is fibers. This was introduced in Ruby 1.9. This is our version of userland cooperative threading. These are our virtual threads, basically. We have all these different call stacks. We can swap in and out of them as needed. We're seeing more and more use of this in JRuby. Early on, it was kind of hidden behind the scenes, now being used more as structured concurrency, large-scale servers that need to handle thousands of connections, ideally not having to write your own I/O reactor for those. The main example, the hidden example, is for external iteration. JRuby collections typically use all internal iteration, where you pass a closure in, pass a lambda in. So that's the standard mechanism for doing iteration over a collection in Ruby. Now, we would like to be able to pull that off as an enumerator concept, an external iterator. The only way we can do that is by having a coroutine, a fiber, drive that internal iteration, and we pull elements off it one at a time. This actually ends up creating a fiber behind the scenes. So you can imagine in a JRuby application, if we don't have a virtual thread implementation, every time you start using these external iterators, we're having to spin up a thread to basically just drive that internal iterator. We heard a bit about structured concurrency in Loom. JRuby folks are also looking at something similar. This is sort of a pseudocode representation of what they're doing in the Ruby world. Grab a socket off of a server, toss it into a fiber to handle the request, and that fiber just does normal blocking calls. Internally, within the JRuby runtime, they have their own scheduler that will deschedule fibers that are blocking on I/O or blocking on locks. Eventually, they're ready to do work. They can be rescheduled onto a native thread and continue from there. And this is now becoming a popular way to run high-scale Ruby servers. So we obviously need to be able to handle many, many fibers on JRuby. So what does that implementation look like? Well, fibers on JRuby before 21, the only way we could do it was by having a native thread per fiber. Now, obviously, this doesn't scale beyond a couple thousand fibers, and even at more than a few hundred, we're starting to introduce contention at a CPU level, at an operating system level, that really hurts our performance. We also have to do extensive contortions to clean up these abandoned fibers. If you iterate partway through a collection, well, there's still a thread out there waiting for you to ask for the next item. So we have to have a way of interrupting it, telling that thread we're done with it, let it bail out, and then finally be collected. A lot of this is being improved significantly. In 21+, JRuby will, by default, use virtual threads for fibers. Very few changes were required. And it turns out that our existing work to avoid using object monitors, because we need to be interruptible, we need to be able to integrate better with Ruby flow control, we haven't run into any monitor issues either. This is basically the change I had to make in JRuby to start using Loom virtual threads for JRuby fibers. This was all I did, and suddenly it started to scale up to hundreds of thousands of fibers very easily. Very exciting. I don't know if this says something about JRuby or it says more about Loom and the work that was done, but I had a whole week set aside, and this is about 5 minutes worth of work. So now, does it scale? That's really the important thing. I've got a little benchmark here. So we're going to spin up a certain number of fibers. That's the number along the bottom. We're going to resume them and get a value back 10 million times and see how long it takes to do that back and forth with however many fibers. We're not quite up to the point of running as fast as JRuby does. JRuby, without a lot of these same parallelism and concurrency concerns, can jump in and out of their fibers very quickly. And they've got very optimized code that basically just jumps from stack to stack in just a couple nanoseconds. We're more at a point of like 4 or 5 microseconds. Again, still pretty good, but we're not comparable to what JRuby's doing here. This trend kind of continues. We stay pretty flat over time by adding more fibers into the system. At this point, of course, the native thread version just falls over. We can't do 10,000 live fibers when they're all backed up by a native thread. So now Loom is clearly winning just because it works. Now, interestingly, JRuby starts to fall off around 100,000 fibers. Now they are the slow one, and it's starting to be too much bookkeeping internally for them to be able to make this back and forth transition for all these fibers. Not exactly sure what's happening internally with JRuby here, but Loom is clearly winning at this point. And then once we get up to 1 million of these, now we're both starting to have problems. Again, we're still talking about on the order of 13 microseconds for each of these operations, but we're starting to hit a wall as far as high throughput with this implementation. Now looking at if we were to be creating these fibers very frequently, of course JRuby comes out ahead again. There's a lot of extra overhead each time we create a virtual thread, and I'm hoping that we can see this reduce over time as well. Not typical that you're going to be creating lots and lots of fibers very quickly in a loop and then throwing them away, but that's a potential model we might start to see Ruby folks take on when they start treating these as just a plain old coroutine. So Loom and JRuby, it's almost exactly what we need. It's really close to solving all of our problems. It clearly makes many fibers possible. The handoff performance really isn't that bad when you look at it from a practical perspective. This was a worst case benchmark. Just going back and forth to the fiber, doing no work with the result. Normally, we're going to take that and it's going to be a request that comes in that we process. We need a response. We send it back out. So a couple microseconds at that point is probably not going to show up. It really solves a bigger problem than we need, though. What we're looking for is essentially just a coroutine. Maybe we wanted Quasar back in the day. Maybe that was the way that we wanted to do this. Maybe we wanted what Kotlin and Scala do, where we bytecode weave and fake the coroutine, fake restartable frames. Difficult to do across dynamic invocation boundaries, but something that could have been done. We're really implementing coroutines on top of virtual threads, which are themselves implemented on top of coroutines. And now with Ruby's structured concurrency, they're implementing a fiber scheduler, which is we run on top of vthreads, which has its own scheduler. And so, of course, there's this mismatch, and we lose a little bit every step of that way. If we could get in there and actually say, the Ruby scheduler is going to be our scheduler for this application, we'd cut out a lot of the middleman and probably see most of the JRuby advantage disappear. Okay, summarizing this work here. So the JVM is a quirky runtime for building a language, but it's really powerful once you know how to manipulate it to do the things that your language needs to do. Invoke dynamic works extremely well, and it gets better all the time. Lambda forms notwithstanding, we really are pleased with the results. I generally can count on it to inline and optimize the way I expect, and I'm getting better at seeing where it doesn't. All of the recent interest in startup time and footprint are very exciting to us, obviously. People ask me why JRuby has not taken over more of the Ruby world, and it's 100% it's startup time. That is the 100% reason. There's no other problem. Like C extensions aren't even it. We've got all the key stuff ported. We can use JVM libraries. It's startup time. 100% is the problem. Panama is already starting to look really good for us. I'm hoping to hit it more over the next 6 months and feedback a little bit more with the team, see where it's working for us and where things need to be improved. But I have no doubt this is going to make our native side, native story considerably better. And like I say, Loom is like a 90% solution. So I'm planning to work with the Loom team a little bit more closely to explain our needs from a Ruby perspective and help that feed into the future development of Loom. And like I mentioned before, every other talk here is potentially useful in JRuby. And I would love to use JRuby as a test bed for all of the stuff that all of you are doing on the JVM. It's really cool. I'm super excited that I'm able to be in this position to try all of this stuff out. So future work. So JRuby Future, like I mentioned, we were largely caught up with current Ruby compatibility. We could actually release Ruby 3.4 compatibility before Ruby 3.4 releases. We're basically aligned with their head, with their tests, and running almost everything. That's freed us up to do things like making a big jump forward to 17 or 21. Probably not any further than that at this point, but we're going to start tracking newer versions of JDK over time. I'm really excited to take all of that work I used to put into compatibility and start looking at more aggressive optimizations, see if we can narrow the gap with Truffle Ruby without the according memory increases and warm-up increases. And really, if Ruby succeeds, there's no reason JRuby can't continue to succeed. There's not a lot of hype about Ruby and Rails these days, but you go to just about every little startup out here and somebody's doing something with Ruby to get an application up and going quickly. We can make that first round application be the scalable application if we can get all this stuff running well on JRuby. And that brings me to the hardest problem for JRuby. I'm unemployed now. I am actually done with Red Hat. They kind of walked away from the project, had other priorities, and I can't complain too much after 12 years of funding. But as of about a month ago, I am not working for Red Hat anymore. So it's basically just me. I have some sponsors on GitHub helping out. I have spun up my own company to start doing commercial support for JRuby users, and we've got a good half dozen to a dozen companies that are already starting to buy in and help fund this. But going back to our first talk here, talking about the tip and tail. People pay for the tail. They pay for me to keep JRuby working well. They pay for me to do releases of end-of-life branches that we don't support anymore. I still want to work on the tip, which is all of the fun stuff that we've been doing here. And I need to figure out how to balance that work with the paying work that is the boring maintenance stuff. So if your companies have open source grants or research grants, or you're interested in JRuby being a test case for some of the work you're doing, please reach out to me. I am working on this stuff every day. I'm still doing it full time, and I've got about a year or two before I have to decide whether this works or not. JVM LS future. What happened to my DaVinci machine? That was the first thing we talked about, was getting the multi-language JVM to be the target for new language development. I want to get these people back in the room. I want to get the Scala folks back, the Clojure folks back. I want to see a Rust-like language on the JVM come here and talk to us about doing an ownership model on top of the JVM model. We need to get those languages back in the room to see what the next generation of the JVM needs to be to support these programming models. We've proven that we can have really weird languages be successful and run well on this platform. And we want to go on proving it. But we need to get all of these people back in the room. We need to get the language part of JVM language back into the discussion. And that's all I've got. There's my contact info and links. Please sponsor or let me know about any open source grants that you might have. If you're running anything with JRuby or know someone running JRuby, I'll definitely take their money too. So that's what I've got. Thank you.